So there was this debate at Galileo's time about falling objects, specifically the rate at which objects fall. According to the Aristotelian notions, large objects, or rather heavy objects and light objects, right, would both fall at different rates because of the greater presence of earth and more presence of air, etc., etc. This question about rate of falling objects presented Galileo with a very interesting possibility for experimentation. Of course, one very simple way in which this can be handled obviously would have been to have somebody and then drop an object on their heads. Okay, so if the same object were to be dropped from a much greater height, okay, you can't see it, it's too high up. Then the amount of pain that is caused when the object falls would have told them that objects keep increasing their speed when they fall. Okay,
so instead of heads they could use something like wet clay, because like that would hurt,
which was what was done much later when we came to the concept of kinetic energy. But I'm just kind of making a whimsical experiment in which they could say that if objects fell at the same rate, then this object and this object should not have any significantly different impact on the head. Okay, so that the question about falling objects was therefore something that was present for quite some time at that time, and a lot of people had a lot of questions about it. Now, sorry, there is a bunch of babblers over here.
Babblers.
Outside the back door making a hell of a racket. Okay. I think they realized there was a class going on. They have left, I suppose. There is this famous debate that occurred in which it was said that objects with different weights will fall at different rates, and Galileo, because of some work that he had done, some experimenting that he had done, he had come to the conclusion that objects which are of different weights but made of similar materials both fall at the same rate, which means that if you drop them from the same height, then they will fall to the ground at the same time. You cannot compare objects very light like a feather and a and a pebble or a stone, but you can compare a pebble or a stone with a much larger pebble or a stone. That seemed to be a more fairer comparison of this. History tells us that in order to prove this, Galileo went to the top of the Leaning Tower of Pisa and dropped two objects. Well, I just want to ask one simple question. Why go to the top of a Leaning Tower of Pisa?
Because it's very high.
So like if something is falling faster, then it will get time to get a greater distance, a greater margin by which it is falling faster.
So one thing is that you go to a tall tower so that you can drop it from a great height and actually observe what happens. Because when objects fall closer to the ground, and you can try it, keeping an object like 5 feet, 6 feet from the ground, you cannot quite make out whether one object fell first or another object fell first. The amount of time difference that seems to be there is not enough. So naturally they would have proceeded to greater and greater heights, and the Leaning Tower of Pisa seemed like a good height to drop objects from. But was that the tallest tower that was available at that point of time? Why choose the Leaning Tower of Pisa?
Because it was leaning, so if we threw the object, it will go straight.
I do not know the
Yeah.
answer to that question, but it makes sense to think like that. That well, if you go to the top of the Leaning Tower of Pisa and you dropped objects from there, then you could be sure that the object is not going to hit something on the way. Whereas if you had a straight tower, right, and you drop the object from the top, it might hit the window or something, or whatever is there along the way, and you wouldn't be able to observe it straight. I just made that up. That's not part of history.
So you also could not see it going. Like if it was a straight thing,
Yeah.
you would not see it
Yes.
going clearly.
You wouldn't be able to see it very clearly. Okay, so it makes sense that way to choose a leaning tower, and it's lucky that you have a leaning tower like that. Yes, Siddharth.
Could be because he was born in Pisa, so he would be living there. So why he would travel?
Yeah, it was just luck that there happened to be this tower in Pisa, which was tall and was leaning and was very useful for this experiment. Now, the surprising part about the whole thing is that there is no written evidence whatsoever that Galileo ever performed this experiment. In fact, what it seems like is that from the records of third persons who made the observation, is that there was a rival of Galileo. I don't know rival in what way, whether he was a political rival or was he a philosophical rival, I'm not sure. But this person seemed to have conducted this experiment more in order to prove Galileo wrong. Okay, so the story goes, and it's just a story, so I don't know the historical verification, I don't know the historical fact of this, whether it is a historical fact, sorry. But apparently, in order to prove Galileo's statements wrongs about falling objects, this gentleman decided to hold a public demonstration. So he called a large number of people, okay, and attempted to perform an experiment that would prove Galileo once for all wrong. And unfortunately, in this case, it just became a public spectacle that happened to prove Galileo right, because when cannonballs, apparently the experiment was conducted with cannonballs, when lighter shots and heavier shots were dropped, it was found that both shots simultaneously came and hit the ground, thus proving that objects fell at the same rate, regardless of their
Same
regardless of their size. Okay, so this was already putting a dent into the Aristotelian ideas that happened to be in existence at that time. But Galileo had to go further than that. And so now I'm going to talk about a serious experiment that was conducted by Galileo, okay, which was as follows. So Galileo's questions were far more important than whether two different objects fell at the same time or not. I suppose that he would have concluded long ago that it is true. What Galileo was concerned was whether objects that fell at the same rate or not.
Sir?
And if they did or they did not, how to prove it. Yes? Yes, somebody wanted to say something?
Yeah. Where was Galileo doing all his research?
I'm not 100% sure, unfortunately, but I think it's definitely in Italy, but I'm not sure whether it was in Rome or in Pisa.
Oh, okay.
So I'm not very sure.
Why Rome?
Huh?
Why Rome?
Rome is part of Italy.
Yeah, but he was in Pisa, right?
Yeah, I do not know. That's what I was saying, that I'm not sure whether he was in Rome or in Italy or in Pisa. He was in Pisa. You're sure about that? Or you can easily Google that.
Yeah.
Okay, somebody just Google that and verify it too. Who asked the question? Anandita? No.
Ruhani.
Huh?
Can you
Ruhani.
repeat?
Ruhani, okay. So the question that Galileo asked was far more complicated to answer, which was that when objects fall, is their velocity uniform or not? Okay, so when you drop objects, the speed with which the object was moving somewhere around there. So let's say that you drop it from rest at point A. That's confusing because that looks like the object itself. Let's say point A, point B, and point C is just before the object hits the ground. Just before. Okay, so now Galileo's question was, once you let go of the object, the speed at B and the speed at C, are they the same? And if they are, how do we know? And if they are not, how do we know? The problem was there was no way, you didn't have good enough clocks, timepieces basically, in order to measure the speeds. In fact, if you try to conduct this experiment yourself, you will find that it's a rather difficult experiment to do. They didn't have accurate enough clocks, and of course they did not have high-speed cameras. Whatever had to be done manually. But even with a high-speed camera and very good clocks that we happen to have today, this experiment is a fairly difficult one to conduct. Okay, so Galileo had to rely on secondary methods in order to answer this question. So he realized that the objects, when they fall too fast for him to be able to make measurements. So he thought, okay, I should slow these objects down in their fall somehow, and then maybe I will be able to make accurate measurements. So one simple way in which he was able to achieve this is by using a simple inclined plane. You know what's an inclined plane, right?
There a ramp?
Yeah.
So like a ramp.
Like a ramp. Yeah. Exactly. So if you make an inclined plane like that, and then you rolled the object down, right? So this object is now going to roll down this path
To B and then to C.
Okay, and then reach the bottom, right? Now the object, when it is falling down this inclined plane, is not moving as fast as it were falling over here, right? That depends on the angle of the inclined plane. And of course, you can keep increasing the angle of the inclined plane. When you increase the angle of the inclined plane, then the object would
speed becomes faster.
It becomes faster.
Yeah, then it becomes faster and faster, right? And actually, if you think about it, the object that is falling straight down is just an example of an inclined plane that has been made vertical.
290, yeah.
Okay, except in that case, you don't need an inclined plane anymore, so you can remove it. But if you keep bringing an inclined plane down and actually make a smaller and smaller angle with the horizontal, then the movement of this object can be slowed down considerably. So he realized that an object rolling down an inclined plane was also an example of a falling object, except you are controlling the fall of the object. Is this clear? Do you buy this argument?
Okay. Yeah.
Yes, I buy the argument.
I buy
And
that.
it's
Okay,
it's
good.
not actually like, it's not falling, right? It's like rolling.
Yeah, it is rolling, but it is going from one height to another height. So
So he said that we just tilted the 90-degree thing and it's just falling at an angle.
it's just falling, but it's falling at an angle. At the end
Yeah,
of
I buy it.
At the end of
He could have taken a
$100. I bid.
What are I bidding on?
It's too costly, but I'll buy it.
Yeah, sir, bought it.
Yeah.
Say that it fell by that
Got
much.
it.
Okay, and well, he logically proved it by saying this, right? So if I have an inclined plane like this, it's exactly perpendicular to the ground. Then if that is falling, then if I incline it a little bit, maybe 89 degrees, and I drop it, you would say, yeah, it's still falling. Then 80 degrees, then you would say, yeah, it's still falling. Then bring it down to 20 degrees, and then why can't you call this falling?
Yeah, or even the ground level.
But if you keep it at the ground level, then it is already at the ground level. Then it will not move anymore.
Or 10 degrees.
Yeah,
1 degree.
but if you even make a 1 degree slope, then it should still, provided its both surfaces are sufficiently smooth. Okay, then it should move. In fact, you know, the Romans, and much before the Romans, the Indus Valley civilization, we had this underground drainage system, right, in our cities, in the Indus Valley civilization cities,
Yeah, sir.
between India and Pakistan. So one of the signs of these being urban areas, what we call as historically as urban areas, is the presence of a drainage system. And if you think about it, drainage systems cannot work unless you work out an angle, a slope from one point to another, correct? Because water goes into the drain, it has to flow, right? And the drainage systems, you just find out at what angle these drainage systems were made during the Indus Valley civilization and also by the Romans. Okay, then you will see. I just remembered that because we said that even if you make a 1 degree angle, there has to be a slope, and an object sufficiently smooth will flow from one side to another, roll in this case from one side to another. So having made this argument, beg your pardon, Galileo proceeded to work with inclined planes. So inclined planes gave Galileo an opportunity to control the falling of objects and therefore to attempt to explain whether falling objects fell at the same speed or did they become faster and faster. And if they become faster and faster, then can you actually do a measurement of how fast they became fast? Listen to what I'm saying. A measurement of how fast they became fast.
Yeah, sir.
The fact that it goes faster and faster is easy enough to prove. You just take a book and you drop it from different heights to the top of your head, and the greater height that you go to, the more it pains. So you know definitely that the book is traveling faster and faster from greater and greater heights. Okay, but the rate at which that increases, that is still in question. Yes, questions please.
So can you repeat that faster sentence again?
So the question that Galileo was attempting to answer was that we know it's moving faster and faster. How to prove it? Point number one, without breaking people's skulls. And point number two, at what rate does it become fast? How fast does it become fast? Okay, so for that he had to conduct some experiments, and the inclined plane proved to be extremely useful in this case. So he apparently built some very beautiful equipment. He was a master workman, craftsman himself. He was good at metal work, he was good at woodwork. And I can imagine why, because he constantly worked on equipment. He wanted equipment with which to be able to conduct experiments. Okay, so he said to have made an inclined plane, a very large inclined plane, maybe in comparable to a man's size, it's kind of like that big. Okay, it kind of bent over here.
Of wood, right?
Yeah, made out of wood and metal. Okay, so he employed some of the best woodworkers and the metal workers of the time to do these kinds of tasks. Okay, on top of this ramp, he put very highly polished, must have been copper, but I'm not very sure, some metal, a rail. Okay, the rail was kind of something like this. When you see the cross section of it, it's kind of something like that. And he made very, very smooth metallic spheres, okay, which could then roll down this ramp. And the reason why he made
So
these
what's
metallic
the
spheres,
thing?
Understand the man standing in the cave kind of things.
nothing comparative in size. So I'm saying that he did work with large inclined planes, not with small little tiny inclined planes. That's all, nothing else.
I didn't get the rectangles there. What are they?
So basically, there are two long lanes, and uske beech mein the ball is rolling.
Got it?
Oh,
Right?
that in front of it.
Yeah. So this
So
is
that the wall doesn't fall out.
front view.
I get it.
Okay. So why did he do that? Is in order to reduce the contact to the minimum. So between the object that is rolling and the rail, the metal rail, the contact points are very, very small, so that you can
So that
have
he can reduce the friction, right?
smooth rolling down. Well,
But
we
they are two.
know about friction. Actually, the result of these.
Sir, he mentioned another animal.
Sorry. And then I like to imagine it like this. I don't know if this is historically accurate, but I would like to imagine. So this was the experiment in which he wanted to show that the object does speed as it rolls down the inclined plane. Okay. So I would like to do it, show it something like this. What I did was I kind of put a string tied to the top, and then I dangled tiny little bells, okay, at equal intervals. So I have to take some equal intervals over here. This is, of course, not historically accurate. I do not know if he conducted the experiment in this manner, but this just kind of illustrates what he was attempting to do. So if you rolled this object down the inclined plane now, then what would you expect to hear if, as the ball rolled down the inclined plane, it rang each one of these bells?
The bell ringing at the same timings, like intervals. That's
I
nice.
don't know. I would
Beat,
expect
like a rhythm.
Right. So the assumption was, since the bells are kept at regular distance intervals, if the ball is moving with the same speed, then you will hear the bells also at regular intervals of time. So you will hear ting, 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 ting.
Like a beat.
Right?
Like a beat.
Yeah. But what do you
Rhythm.
think he heard?
A single ring.
Ting, 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 ting.
Ah.
Something like that.
Well done. Somebody actually did it. Then thankfully I didn't have to do it myself, because it sounds awful when I do it. So if a ball were to move with increasing speed, then what will happen is, because the ball moves faster between every successive bell, the initial time frame will be lesser and the time, will be more, and as the ball falls further and further, the interval of time between each successive bell will reduce. So it might go ting, 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 ting. Okay, that was too many bells. There aren't enough bells.
Like a bomb blast beep.
Okay, which naturally then gave conclusive evidence that when objects fall, they speed up. Okay, and this did not, of course, show you some way in which to measure the rate at which the speeding up takes place. That at that point of time was not possible to do. So we have to wait until Newton came around to figure that one out. So the experiments with inclined plane continued for Galileo, because he was not just satisfied with answering one question. Whenever he answered one question, it throws up many such questions. And in proceeding with his experimentation, he came upon the first concept that we are going to visit, a concept so simple yet so important and so profound that we cannot learn Newton's laws without understanding that concept. So what that concept is and how did Galileo come upon that, we will see that in the following class.